Hello.
Hello.
Hi, Austin. Can you hear me well?
Yep, can you hear me?
Yes, I can hear you. So, hope everything went fine last time. It was just a false alarm, I hope.
Yeah. Thank you so much for rescheduling.
Okay, no problem, no problem. Good to hear. It was just not an important thing. So I'll make you a co-host,
hmm
uh, or maybe I should just allow you to share so you don't get disturbed by new entrances. Let me check if I can just allow you to share. Oh, yeah, you should be able to start sharing.
Yep,
Let's try that.
sure.
Are you able, or should I change something?
I should be able to. Do you see it?
Yes, I can see the screen, full screen. Great, I can hear you well.
Nice.
So then I think everything's ready, and now we wait for a few minutes for people to join.
hmm
There are some in the waiting room, and then I can introduce you afterwards, and you can start after that.
Sounds good. Thank you so much.
Okay. Great, looking forward to the talk, and let's start in a few minutes.
Yeah.
Thank you.
Hello, Joseph. Can you hear me?
Hi, Shagning. Yes.
Hi. Yes.
So
Can
we
you
just wait for,
introduce? Okay.
yeah, we
Wait
just wait for a
for.
few minutes.
Okay.
You want to do the introduction or should I go on?
You can go.
Okay, thank you. We just wait until 4:05 and until people
Okay.
join.
Okay.
Thank you. Yeah, I think we can start. So hello, everyone. Thank you for joining. And something changed. So Oswin, can you still share your screen? Yeah, so thank you for joining on the Same Reinforcement Learning Seminar. Today we have Oswin So from MIT giving a talk on solving stabilize avoid optimal control via epigraph form and deep reinforcement learning. So Oswin So is a first-year PhD student in the Department of Aeronautics and Astronautics at MIT, working under the supervision of Chu Fan. And he received his bachelor's from Georgia Tech. His research interests lie in the analysis of reinforcement learning from the perspective of control. So thank you for joining us today, and you're welcome to start with your talk.
Yeah, thank you so much. And thank you so much for organizing the meeting after last week. But yeah, my name is Oswin, and I'll be presenting our work that was recently accepted to RSS on solving problems with stability and avoidance specifications that combines constrained optimal control and deep reinforcement learning. So in robotics, many of the tasks that we want to solve have multiple objectives that may conflict with each other. One prominent class of these multi-objective tasks requires stabilization to some goal set G, while avoiding some avoid set A, which we denote as the stabilize avoid problem. For example, take this helicopter. Our goal here is to arrive at some destination while avoiding crashing into the void set here, which we denote as the mountains. So this is just one example. But more generally, the problem that we want to solve is given some specification of some goal set and some avoid set, how do we find a policy that satisfies these specifications? And so to start off, what we can do is, given the goal set G, we can construct a stage cost function, L, that is 0 on the goal set and non-zero outside. And one simple example of this is LQR. If we use a quadratic stage cost, then we get a controller that gives us system trajectories that asymptotically stabilize to the origin, 0, 0, as shown in this figure on the bottom. And previous works have shown, actually, that a policy that minimizes the stage cost summed over an infinite horizon will result in a globally asymptotically stabilizing controller, given some technical assumptions on controllability and detectability. However, this only addresses the stability part of the specification. We might also have a safety part as well. For example, we might want to avoid entering the red region in the LQR example. And so to tackle this, in this work, we take the previous result on asymptotically stabilizing controllers and additionally consider a safety constraint to our infinite horizon optimal control problem that restricts the system from entering the void set at all times. So if we go back to the LQR example, then what this might look like if we also add in the additional safety constraints is we get the purple trajectory, which does indeed stay outside the unsafe region in red, as opposed to before. And so by adding safety constraints to our infinite horizon optimal control problem, this restricts the previous class of stabilizing controllers to also satisfy the safety constraints, giving us safe and stabilizing controllers by construction. Hence, one strategy would be to solve this infinite horizon optical control problem using RL. Then the solution we get will automatically satisfy the stabilizer void specification based on the previous few slides. Now, before diving deeper into our approach, we first visit some alternative approaches that try to solve the similar problems. One example is model predictive control. But there's some weaknesses or some cons with this method. First off, with model predictive control, you usually only consider a finite horizon for optimization, which if the horizon you pick is not long enough, then it's possible to still violate safety constraints. Second, there's a problem of recursive feasibility. That is also related to the problem of finite horizon, meaning that if your horizon is not long enough, it's possible that your next optimization problem is not feasible, even though your current one is feasible. A final, one more a potential issue is that this requires you to solve a trajectory optimization problem online at each step, and this is expensive if you do not have the sufficient computational resources to solve this. And finally, this because you have to solve an optimization problem online, this method is prone to local minima, especially if your problem has nonlinear dynamics or nonlinear costs or constraints. A different method that we could choose is to use sum of squares. So if you have a polynomial system, then you can frame both safety specifications and stability specifications as solving a sum of squares optimization problem, which is a convex optimization problem that you can solve using semi-definite programming solvers. And this works great, except first off, you need a polynomial system, which restricts the types of systems you can work with. And second, this approach scales badly to high dimensional systems, because in the end, you are working with polynomial approximations. And if you want a more precise controller, you need more polynomial terms, and this scales badly as your system state increases. And finally, we might face some numerical challenges in practice when we try to use sum of squares using the current semi-definite program solvers. Another approach that we can take is more rooted in nonlinear control. This is to use control barrier or control Lyapunov functions. And so basically these are certificates that prove that your system is safe or your system will stabilize to the origin if you have these functions. But the problem is that it is, first off, you need to find these functions, and it's difficult to find them in general. But also, if you have input constraints, then existing methods don't really handle these very well. Another problem is that with a common approach is to combine the safety aspect using control barrier functions and the stability aspect using control Lyapunov functions using a joint QP. But this QP can be prone to local minima. There are places where your safety specification and your stability specifications might fight each other, and this might result in your system getting stuck. And finally, if your system is not, say, linear, but it has some general nonlinearities, then it's really difficult to construct in general. And finally, there's also unconstrained RL as an approach. And this works really nicely, except there's the problem of sort of how we can make our policy satisfy the specification that we have. So normally what people do is they use reward function tuning. So you start with some initial reward function that encodes, maybe I want to stabilize to some goal set, I want to avoid some avoid set, but then the policy that you get out of RL might not satisfy these, and so you need to sort of tune the weights of your various components until they actually do. But then even though you might get a policy that does appear to satisfy these specifications, it's not clear whether they actually do on certain other instances that you might not have tested on. And so now we go back to our problem. In summary, we want to solve an infinite horizon constraint optimal control problem because the solution gives us a policy that is both safe and stabilizing. But a big question is that of the constraints. So we know how to tackle the sum of costs part, but how do we tackle the constraint part? And so one option that we can use is we can turn to the constrained MDP literature, because in their problems, they also tackle a very similar looking problem where you want to minimize a sum of costs over infinite horizon or rewards. But then they also additionally consider this constraint where they want this sum of CXK over infinite horizon to be less than or equal to D. Now, these two constraints they look similar, but they're not exactly the same. However, we can still make use of this. So what we want to do is we want to sort of convert our current constraint format into that of used by the CMDP. And so one way we can transcribe it is if we assume that our avoid set is defined as the superlevel set of some function h. And what this means is that our original constraint can be written as h less than 0 for all k's. And then what we can do is we can sum over this max 0 of h for infinite horizon. And we want to enforce that this is less than or equal to 0 for all time. If we do this, then we've effectively rewritten our constraint that we want to satisfy into the form that's accepted by CMDP. If we plug this back in, then this is what we get for the Lagrangian for CMDPs. So you get your original cost function in J, but then you also add this additional term where you have a Lagrange multiplier multiplying the sum over an infinite horizon of your constraint function, but with this max 0 to ensure that you satisfy you don't want any constraint violations for the infinite horizon. But this approach is a bit problematic. And to explain what the problem with this transcription is, we first look at the update rule for the Lagrange multiplier, lambda. So when we update the Lagrange multipliers, we are basically performing gradient ascent on the Lagrange multipliers, or on the Lagrangian L. And if we look at what the gradient of L looks like with respect to lambda, then we see that it's exactly this term that's an infinite sum. But the issue here is that the terms that we're summing are strictly non-negative. And moreover, when safety is violated, the h function becomes strictly positive, which means that if there are any safety violations during training, then the gradient will strictly be positive, which means that lambda is going to be monotonically increasing when you have any sort of unsafe trajectories during training. Now, this is a problem because if we look at the gradients of your policy, then these scale linearly in lambda and also in your constraint violations, which means that if you have any unsafe initial states under your current policy pi, then lambda is going to continue to increase and eventually explode. And because your gradients of your policy scale linear with lambda, then your optimization procedure is also going to explode and become unstable. And so to avoid this problem that you face when using Lagrangian duality as it's done in CMDPs, we explore an alternative approach, which is called the epigraph form. And so for those of you who might not be familiar with the epigraph form, this is sort of a reformulation technique that is commonly used in traditional optimization. And briefly, what we do is we first upper bound the cost using some new variable we introduce called z, and then we minimize this upper bound. So do you see what that looks like? What we do is we first, starting from our initial problem, we first introduce this variable z, and then we want to minimize this upper bound on the cost z, subject to our original constraint, but also our new constraint that the cost is less than or equal to this upper bound that we introduce. Next, what we can do is we can actually combine these two constraints together into a single constraint. So now we just have a single constraint, which is the max of the previous two constraints, less than or equal to 0. And finally, one more step we can do is that we can move the minimization of our policy from the outside with the minimization with z into the constraints. So now what we end up with is a scalar optimization problem in the outside. And then for the constraint itself, it's also a optimization problem that's over the policy. So this is what we end up with. And one interesting thing to see here is that the scalar variable z that we introduce, this doesn't, our gradients with respect to the policy don't scale with z. And so we don't really end up with the same type of optimization issues that a CMDB Lagrangian duality-based approach faces. However, we face a different problem, namely that our problem here has a different problem structure. So instead of a sum of costs over time, as is usually done in reinforcement learning, what we now have is a max over these two terms here, where the first term in red is a max over an infinite horizon, and the second term is just your previous sum of costs over infinite horizon minus the auxiliary variable z. And so because we have this different structure, we aren't able to apply off-the-shelf RL algorithms to solve this epigraph form problem. And so what we do is we still tackle this problem using RL, but right now our cost function, we have a sort of new, you can consider this as a using RL to solve this new cost function, where this new cost function is j tilde and is represented by the terms in above the blue line. And if we want to solve this using RL, then one thing we can do is we can use on policy algorithms. And to do that, we need a policy gradient theorem. So if we have a policy gradient theorem, then we can solve this problem using on policy RL algorithms. Now, so now our goal is to derive a policy gradient theorem for this new structure. One requirement for deriving a policy gradient theorem for your problem is that the value function and the action value function should be recursive. And thankfully, for our problem structure here, it turns out that this is the case. So if we look at our new cost function, j tilde, it's defined as a max of these two terms here. What we can do is we can take out the terms that correspond to time step 0 out. Here we mark them in purple. Then we can use properties of the max to move them into a different term, which only uses information from time steps x1 and onwards. Here we denote this as j tilde of pi. And now, if you look carefully, you can see that in the place where z goes, we now have z minus L of x0. And so what this means is that we can actually treat this as a dynamics for z. So if we define z1 to be exactly equal to z0 minus the cost at time 0, then we get this really nice recursive structure for J tilde, where your dynamics for Z are defined as ZK+1 equal to ZK minus LK. And sort of some intuition for how this sort of dynamics for Z looks like is that you can think of, since Z denotes the upper bound of your total cost, then in the next time step, the upper bound will decrease by exactly the stage cost that you incurred at the current time step. So great. So now we have a recursive structure for our value function, action value function. Then we can use this to derive a policy gradient theorem as like, and the sort of derivation for this is like pretty standard. It just follows exactly the same steps, except now your definitions for your value function, action value functions are now different. And so because of this, the gradient of the cost function that you get looks very similar to the normal case, except you now have this additional difference, which is caused by the max. So instead of an expectation, you now have a conditional expectation, where this conditional expectation is something that can be computed really easily. So great. So using this, we can solve for the policy that minimizes this new cost function. And we also get a value function corresponding to it. And so if I simplify the problem using the value function I get from RL, then we get this problem for the outer problem. And this is a 1D optimization problem that can be, and so we can solve it very easily using techniques such as bisection or something. And so to summarize, our we apply the improvements. So we take the policy gradient theorem to derive an on-policy RL algorithm. We can then use the improvements from PPO to get some PPO-like algorithm, but using our new policy gradient theorem instead of the original policy gradient theorem. And then we finally combine this with an outer root finding problem to solve our infinite horizon constraint optimal control problem. And we denote this entire approach epigraph form PPO, or EFPPO in short. And so very briefly, here's what that looks like. We first use the policy gradient theorem that we prove and the improvements from PPO to solve for a policy and a value function conditioned on different values of the upper bound Z. And this gives us, this gives us a policy and the value function for that policy, which we then use to solve a scalar root finding problem to solve for the optimal upper bound Z. So if we solve this root finding problem for a data set of different x's, then we get a data corresponding labels for each x. And while you could solve this root finding problem online during deployment, we can also train a neural network to just predict the Z star for each of these x's if we want to avoid solving this root finding problem online. And finally, once we have this Z star that we train from neural network, or you can just use root finding, then we can plug this into the policy that we obtained from reinforcement learning to obtain the final stabilized avoid policy. So we now show results from 2 of our simulation experiments. In this first task, we want the hopper to stabilize to the green box while avoid falling down into the red box. Our method on the right successfully completes the task. So our method on the right successfully completes the task, while a Lagrangian duality-based method over-prioritizes the safety aspect and fails to stabilize to the goal. I'm not sure if it's coming across well on Zoom. So we next show results from a simulated F-16 fighter jet. So here, the task is to stabilize to a low altitude flight corridor while avoiding collisions with the wall or the ground. And from this challenging initial condition, our method successfully completes the task, while the baseline method is unable to maintain safety and crashes into the ground. I think these are playing on Zoom as well. So yeah, some takeaways from this work. So the Epigraph form provides a stable way of solving constraint optimal control problems to find safe and stabilizing controls. To summarize the method, we first use this. We can solve stabilize avoid problems by formulating an appropriate infinite horizon constrained optimal control problem. Then we can use the Epigraph form to handle the constraints in a more stable manner in comparison to Lagrange duality-based methods as is used in the CMDP literature. And finally, the Epigraph form has a different structure, which means that we cannot use off-the-shelf RL algorithms to solve. But by deriving a policy gradient theorem, this allows applications of existing on-policy methods along with their improvements to solve the final problem. And you can check out our QR code, which has links to our website with some additional figures and videos. And yeah, thank you for listening to the talk.
Thank you very much for a nice presentation and talk. So now we'll proceed with some questions from the audience, if there are any. So if you have a question, please feel free to unmute yourself, raise your hand, and I can unmute you and ask a question. You can write in the chat, or you can just unmute and speak up if you have questions.
So how do you handle the balance between the stabilization and the reward performance and safety? So in this talk, I knew that you gave an introduction about how to handle the stabilization while ensuring safety. How about the reward performance?
Yeah, that's a very good question. So I guess the basic idea is that if we look back at this constraint, right, then what this constraint is saying is that for the z that we find, it has to guarantee that the constraints are satisfied because we want this max h x k to be less than 0. So for any z that we pick, we have to be safe. But then we also want the z that we choose. If we choose z to be, say, infinity, then the right term becomes negative infinity, and our constraint is just goes back to the original safety constraints, which means that we are basically prioritizing safety over everything else. If we choose z to be negative infinity, then it means that the right term here is going to dominate the max, and so we're going to prioritize minimizing this cost here. Now, these are the two extremes. Instead, we want to find the optimal z, and the optimal z is 1, such that the safety is going to be satisfied because we want the maximum h to be less than 0. But we want to serve of those feasible z's, we also want one that reduces the cost as much as possible. And so sort of the balancing happens automatically by finding the appropriate z that guarantees that these constraints hold, if that answers your question.
Okay, thanks. And which benchmark do you use to test your algorithm, such as the F16?
Are you referring to like a standard environment type of thing?
Yes.
So in this work, we
mm.
actually rewrite our own environments and compare them on that. So like I know there are other examples such as like Safety Gym or something, but we chose
Yes.
not to use those.
Okay.
Okay, thank you. There is one question in the Q&A, maybe a little more general. Based on your experience, what role can reinforcement learning play in the field of control systems? So I guess maybe more the pros and cons using reinforcement learning for the problems you mentioned.
Yeah. So I think like right now one of the main, or maybe there are a few different problems. One is that there's the problem of specification to like behavior. Like, so oftentimes we have a desired behavior that we want our policy to satisfy. How do we, and there's a problem of like how we can transcribe that specification into something that such that reinforcement learning algorithm will give us a useful policy in the end. And I guess this work tries to provide one solution for this problem. But there's also other problems in general, such as like you have your traditional like if you're training a simulation and deploying on real world, there's a sim to real gap, and like sort of distribution shifts. But like although those are some issues that reinforcement learning faces, I also think at the same time that there are a lot of advantages for reinforcement learning. Just because like when you have when your problem is more complicated than like the most simple like linear dynamics and like quadratic cost, then we don't really have very good methods to synthesize controllers for them. Especially if you want to avoid sort of resolving an optimization problem online is in the form of NPC. And so I think reinforcement learning gives us the opportunity for really high performing controllers, but we need to fix sort of the issues of like sim-to-real gap and like task specification before we can get them to like work robustly in the real world.
Yeah, thank you very much. Maybe one question from my side. So you mentioned modifying on-policy algorithms here to incorporate your approach. Is there any limitation of using this for all off-policy, or it's basically something you will address in the future?
So it's actually much easier in the off-policy case. So with the off-policy case, we want to sort of solve for some Q function or some value function. And all you need for that is sort of a recursive definition of your value function or your state action value function. And so all you would need is to let's see, find the slide. So as long as you have this dynamic programming equation, then you can learn this using sort of a TD error or something like that. And that will allow you to apply off-policy algorithms really simply. The reason why we chose to use on-policy algorithms in this work is due to sort of the better stability properties of on-policy RL as opposed to off-policy RL. But yeah, definitely if you're concerned about like data efficiency issues, then off-policy algorithms would be a good idea to try with this approach.
Okay, thank you. Is there any other question?
Yes, thank you. I do have another question about the mentioning that you had on exploding lambda effect in Lagrangian methods. And basically that behavior for example, for trajectories that are defined by the Lagrangian methods becomes maneuvering around the safety region due to that. So usually it goes until the border of the safety constraints and then it finds a detour. And I want to see that if your method with epigraph forms find a more smooth trajectory compared to that because of this dual optimization, or it also behaves similarly. Yeah.
So I guess just to repeat your question to make sure I'm understanding correctly, with Lagrangian duality-based method, the trajectory might like get close to the safety boundary and then veer off a lot because of the penalties, and you're wondering if the Epigraph form approach will give more smooth trajectories.
Yes, yes. So if the epigraph form becomes more similar to vector fields, for example, yeah, something like that, like Lyapunov methods, or is it in behavior or in the optimized trajectory solution at the end? Yeah.
So in our current formulation, we don't really have any, or we don't particularly target this like smoothness problem. So the resulting trajectories you get from this method are basically going to be solutions to constraint optical control problems. And so they will, so if your safety constraints and your sort of your performance are sort of contradicting each other, then it will get close to the boundary to optimize your performance. And so you could add in terms to your cost function to address this by, for example, penalizing unsmooth behavior by like maybe like having costs on like high derivatives or something. But like on its own, this framework is very general. And the default behavior, if you don't specify any of those like regularization terms on your control, will be a basically the solution to a constrained optical control problem. If that makes sense.
Okay, is there any other question? Yeah, I think that's all. So thank you very much for a very nice talk, and I'm happy we could do it in the second time after the last unexpected cancellation. So okay, then we have one final question, since it seems. How did you validate or verify this work of simulation? I guess here the question is more whether you have tried this on a real system also, or if you
yeah, that's a very good question. So in this work, we only ran simulation experiments, but we're currently working towards testing it on hardware, just to validate these like findings and see if like how sort of sim to real gap affects this type of algorithm.
Okay, I think that answers the question, and I have already sent in the chat our link to the next upcoming seminars if somebody of you in the audience wants to subscribe to the mailing list or check the next talks. So I think if there are no other questions, I would like to thank Austin for joining today and sharing his work, and looking forward to updates on your progress. So thank you very much for joining, everyone. And in about a month, we'll have our next talk. Feel free to check the website and subscribe to the mailing list to get the next talk invitations. Thank you very much for joining, and see you soon, I hope.
Thank you.